Hopefully this won't be too long, but another true slit video. Yeah, I just wanted to finish up on something, just to, some other observation I had, just to clean this up completely, because I really think I got it all. So Carla, of course, naysayers here. If your theory would be right, then there would be no interference pattern with two slits, but instead you would see the sum of the patterns you get when you first open only the first slit and then only the second slit, shooting one electron at a time. Right. Well, that's the problem. Is that this whole phenomenon is created by the slit, the pedestal, the thing in between the two slits is what's creating the interference pattern, because it's the thing that has a signature on its sides. It's vibrating differently. So the point is that in the damn, I always do this. This poor digital frame. I've knocked it over about, I don't know, 47 times now. 47, something like that. 47 times. Yeah. I don't know why. What's this damn chair? Well, it's the damn filing cabinet, actually. Anyway, I have to move some shit, and I don't want to. So where was I? Okay, so let's do the picture to the whiteboard. Anyway, all right. So here's the catch. Here's the slit, right? And then here's the outside, and then here's the outside. So this creates your double slit, technically, right? You have a thick material, and a thin material in between. And the problem is when you create a single slit, is there's no way to create a single slit and retain a thin slit, right? So when you have a single slit, you're always going to end up with two thick slits. So clearly this surface, the thickness of this, the width, is a phenomenon of importance here. So here's my argument. Let's look through this from like looking at overview. Is you have this gun shooting something, then they take a tiny hole. Okay, so we're looking from the top down, and a tiny hole that shoots more, that also creates a spread, a certain kind of a uncertainty. So there's an uncertainty created here. All right, but the key is that this thing might have a pattern, which I'm going to demonstrate with a laser in another video. That the deflection is sometimes patterned depending on this hole. So I mean, if this is a pinhole, I think you will get some sort of rings. So anyway, my argument is that here's your single impediment, and then your walls on either side. So technically it's not the two slit experiment, it's the single impediment experiment. And what's really happening is this focus here is intended to actually create light, like this circle that concentrates, like 90% of the light, let's say, hits between here and here. It doesn't hit these exterior surfaces, or it does so in a minor way. So only 5%, let's say, hits either one of these surfaces. So the whole point of the experiment is to concentrate the light on these surfaces, to hit these surfaces, to interact with these surfaces, and only to allow a very, barely enough room for a photon to get through here. So you create an obligation to interact with this interior surface, a high probability of interaction with the center impediment. So that's why you get this effect. So let's go back to the Newton glass, right? This is back to Newton and the glass thing. So what Newton found was, as you change the thickness of glass, right? If you go from a thin, you just keep scraping off a layer of glass, you'll change the reflectivity of the surface of the glass. So the glass becomes more or less reflective. So this piece could be only 4% of the light reflects off of it, and this piece, it could be up to 16% of the light reflects off of it, just because of the thickness. The probability of reflection for an individual photon. Now, what was the obvious problem here for Newton was, well, what's the theory? That light goes to the bottom and figures out how thick the glass is and then comes back up here and decides to reflect. I mean, that doesn't really make any sense, right? And even Feynman, I should get the clip from his video. I mean, I should do that. I'll do it in the future. But Feynman talks about this experiment with the glass and refraction. And Feynman, points out this conundrum, this paradox, by basically saying, well, how could light, what does it do? Go faster than the speed of light to get to the bottom, and then tell the photon to then go back to the surface and reflect? I mean, that just doesn't make any sense. How does it know how thick the glass is? And my argument is the electrons that make up the glass know how thick the glass is. Okay, when the atoms are inside of this, they are arranged in arrangements that are standard, and they can only move so much, jiggling back and forth because of this thickness. And as you change the thickness, you change the position of these atoms, which changes the electron voltage or pressure of the surface of the glass. So you're changing its electrical potential as you change its thickness. And that signature is on the surface of the glass. That is readable by the photon. So essentially, when the photon comes in here, it's interacting with electrons on the surface of the glass that know how thick the glass is. They are reflective of the thickness, in that their frequency is changed because their movement is changed. Their vibration has been changed. Based on how thick the glass is, it will vibrate more quickly. So the thinner the glass, you can almost imagine, can do a higher frequency than a very thick piece of glass would be a very low frequency. And that frequency is part of this harmonic. But the point is you go through this range from 0% to 16% reflectivity, and so you're basically just rotating constantly through this clock of change. So you have a 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock position, and you could just argue that this is the 16, this would be the 0, this would be the 8, and this would be the 8, kind of a thing. Or 4 and 4 would be the more correct, in terms of the percentages. And it just depends on what position these atoms end up being in. Or, like I said, it could be something more fundamental to the electron. I can't say which one it is because I'm not sure. I don't know whether it's the vibration of the atoms itself or the spin of the electrons, but something's affected by thickness. Alright, so anyway, back to the two-slit experiment. So the argument is that this is vibrating, big, and this is vibrating small. So this has small item electricity, this has big item electricity. So the electrical potentials on these two surfaces is different. And it's that difference in electrical potential that is creating the effect. So the point is that when you have one slit open, you're automatically stuck with two heavy items on either side of this, to form the slit. And so there is no thin item, so that's not there's nothing to create the banding, and that's why you get the bulge effect, is because you have no thin item to correct this thin item is what's creating the banded pattern. Just like in the glass, there has to be the right thickness to create this full 16% effect. So the thin item here is perfectly is the right thickness to maximize this 16% thing, and the 16% thing is what makes it go from this 4% thing to this 16% thing. You know, where 16 is possible because you have these zeros now. And so that's why closing one slit, that's why you have these dark bands in the two-slit experiment. Let's just consider them dark bands. And the argument would be with one slit open, so here's one slit, and the dark bands represent two slits. So one slit is this line, and the argument would be, how can you go from this pure straight line where, okay, you have a photon at this position here, well, with two slits open, there's no photon there. You have darkness. So how would that be possible? Well, it's possible because you don't have the same surfaces anymore. The one slit experiment has no thin surface for photons to interact with, and that's why it's not banding. So theoretically, what I'm arguing is you can't do, if you could theoretically prevent photons from going through this side but keep this thin slit, so which would require like I have to create an experiment that demonstrates it, but I think you might be able to get away with it. See, it's very hard to create a surface in front of the slit that won't also cause diffraction. But I mean, theoretically, here's the two-slit experiment again. I mean, the two slits anyway. The 90% of the photons are coming through here, you know, interacting with the center pedestal or post. And the idea would be is not to block this slit, but to create a barrier a little bit canted. Okay, so now any photon that was coming that was going to interact with this side of the pedestal would now be blocked, and so then only photons that were on this side of the pedestal could interact. And I would claim that if you do this experiment, leaving this a pedestal and blocking in front of the pedestal halfway, the dimension halfway on the pedestal, so now it's more difficult for a photon to get through this slit. Obviously it's still going to be able to curve around here and go like that, but that noise would be only 10%, let's say, so it wouldn't destroy the banding effect. And my contention will be is if you do this experiment, you'll end up with, on the single slit, you'll end up with the same banding pattern you get in the two-slit experiment. You won't get this, you will get this. So that would be my proof, is do the experiment and create a shield for the second slit that's very close. It can't be too close because you don't want to create an electrical problem between the two surfaces where they bond electrically, but close enough to prevent much energy from being able to go around the shield and destroy the results. I think it would work theoretically. So that would be the proof, is that experiment, that the single slit will create the bar pattern as long as one side of the single slit remains a thin item, a slit, you know, a small pedestal. So as long as these things are, you know, it's this heavy mass that ruins this exterior wall being able to create banding. It won't create banding because it's too thick. Yeah. So I think that about covers it. So the point is that if you combine these two observed phenomenon, Newton's layers of glass and this two-slit experiment, I think you have an explanation. And the explanation is, again, that electrons are creating the probability wave through the dynamic of molecular structure. I mean, you can imagine it also just by thinking that this is called the electromagnetic spectrum. You know, all of photons, you know, from radio waves to cosmic rays. And so you have to understand that everything has an electrical potential, and that there's, you know, these, you know, this radiation of you know, a field of, you know, weak magnetic field is probably around all matter, and or at least built into the structure of the matter itself, the physical structure of anything that has a mass, and that that is probably explains why, as you go thicker, you change the arc of that magnetic field, and so as the thinner the item, the thinner those the tightness of those bands of alignment energy, or magnetism, or whatever you want to call it, electromagnetic potential, you could call it, would change with thickness. And that's creating the signature, that's creating the information that's telling the photon, forcing the photon to reflect or not reflect. The photon isn't deciding, the electrons are deciding, in a sense, because they're the ones that have the information in their character, in their structure. Okay, yeah, that's probably enough. Yeah, this is done. I got it. I got it. Yay me. Yeah, I like it. So yeah, we'll block this one guy. There's some sort of Christian homophobe, dirty pig, slob, motherfucker. Saying some kind of bullshit here. You know, he agrees. If we want to debunk the experiment, debunk it experimentally, not physically, which doesn't make any sense. So I whatever. You know, he just sits there and says, you know, he invented this before me, and yeah, he's a genius because he, you know, and he should make his own draft science channel based on my results or whatever. I don't know. It's just very rude. But you're just like, why be an asshole? Oh, that's right. That's what people do on the internet. Balls. And by the way, cold fusion is real. You know, so it just spams the damn page with this crap. And I'm supposed to say what? Thank you? Well, I'm not going to do that. So, enough of that asshole. So anyway, till next time. Yeah, I got this. I just have to find, I have to just resolve this mechanism more. See, I mean, I do have this whole thing about the you know, electrons being photons in a double helix, and they're spinning this way. And that's why they, you know, right or left, and that's why they don't move the speed of light, but they can move very fast. It's because the spin is a way of using their speed. But I still have to explain. But we know that they also, electrons have energy levels that are, you know, what it takes for them to release a photon. And so I think it was probably something in that nature. But I mean, this vibration thing is really kind of important, I think. You know, the very idea that if something's bouncing back and forth, and I close the space in which it's bouncing, it's going to bounce quicker. So, if you tune the frequency of this little pedestal to the light, that you're more likely to create this banding pattern. But clearly, you can't create it if you don't have the pedestal. Obviously, two thick walls are going to create a different pattern than a thick wall and a thin wall. I think obviously in the sense that it's an obvious place where you could account for the fact of the difference in behavior. That the difference in behavior between two slits and the one slit is the fact that the one slit always has two thick walls and the two slit has the impediment. Because we're not thinking about the pedestal being, they're calling it the two slit experiment instead of the single pedestal experiment, which can't be duplicated as a one slit experiment. You can't do like I said, you can't do this experiment without some kind of block to stop the, to do it as a one slit experiment without there being some way to prevent photons from getting to this second side. And that's why aiming the photons, well, aiming them should create the effect. So maybe that's another way to fix this experiment, is to aim the photons through one slit and leave the small impediment and just do it by theoretical inevitability that they have to go through the one slit. That might help. But then you still got the problem of the aiming them so they mostly hit the interior wall rather than the exterior wall. So you have to deliberately aim them to hit the interior wall without going over. And that's a very precise aim. So that might be part of the problem, is you might not be able to aim them that thin, that tightly, that precisely. Well, you have to just find some way to, like I said, this thing with the shield would work as a proof, I think. This shield thing here, yeah. This is where I said the shield that goes half the width of the pedestal. Yeah, that might work. Anyway, till next time.